Hello students! Today we're going to be talking about interactions. Interactions are a type of analysis that you do for causal data. It allows you to look at the multiple levels of experiments. So let's say you have a weak strength, or like a control group, and then a weak intervention and then a stronger intervention, something shorter, something longer, and a control group as well. So multiple levels to see how those interact with other variables. So it lets you look, similar to multiple correlation, lets you look at multiple kinds of variables and how they might interact, they might build on each other, how they might take away from each other, those kinds of things. So how do variables interact with one another in a causal sort of way? So let's start with talking about multiple causation and interaction. Multiple causation is when a behavior is caused by more than one or two variables. So you might have even three, so multiple causes. So think about things in the world. There generally are multiple causes to a variety of behaviors. Also, you might hear this as it's multiply determined, it has multiple causes. So that's what we're talking about with multiple causation. There's multiple things that are causing this one thing to happen. So this is the outcome, but it's caused by one, two, three things together. Interaction is how the variables affect one another. So looking at interactions, looking at causation here, we can kind of pinpoint exactly how the different variables are affecting other variables. So if we want to say increase school achievement or decrease smoking or whatever it is, there's probably more than one variable causing the resulting behavior, thought, cognition, things like that. So any one variable alone isn't always the cause of a behavior. It's an easier example to look at. Thinking back to our experiments example, the quiet room and the loud room for test scores, usually it's not just one variable. And so you can look at the causes of, well, maybe we tutored people for 1 hour versus 2 hours, and we put them in a quiet room and a loud room. How do those variables interact? Are you going to do the best when you've been tutored 1 hour and you're in a loud room for some reason? That's what we're talking about. So when two variables interact with each other or act so when you need both together or they interact with each other, that's what we're investigating here. So a practical example of this is, what is the cause of obesity? So think about it for a minute. Maybe hopefully the graphic there is maybe not quite clear enough to actually read, but what are some causes, or what is the cause of obesity? And the answer here is really, there's no single deciding element. There's multiple factors that interact to produce the end result. So it's not just one cause, there's multiple causes, multiple things interacting to lead to obesity. So suburban living decreases walking, fewer meals being prepared at home leads to increased obesity, fast food industry expansion. So these are all different variables that can interact to lead to obesity. Sedentary children due to electronic entertainment. And see, so any one of these might not be the cause, but when you put all of them together, maybe you get obesity. So evolution is another impact here. So our bodies, when we evolved, it's really hard to gather really fatty foods, things that are high calorie, and so we evolved the taste for high calorie, high fat foods to keep us alive. Now it might be easy. I have Halloween candy like sitting on a table behind me. So it's pretty easy for me right now at this moment to go and gather some high calorie, high fat foods. So what do? My body wants those foods. Evolutionarily, I developed to want that candy. So I'm going to probably grab some candy, and I kind of want some now that I'm talking about it. But all of these things together lead to obesity. It's not just one of those things. Just having candy out there, my wife has much more self-control than me and has avoided eating any of the children's Halloween candy. So just because it's there is not the cause of, say, obesity, for example. So another example of an actual interaction are risk factors in childhood development. So we see that for having more and more risk factors, you are at a higher likelihood of problems in later life and adulthood. So whether it be in schools, with relationships, whatever it is, having more risk factors interact together to put you at more of a disadvantage, to give you a harder time developing through life. So things like specific developmental delays, physical illnesses. If you broke your leg when you were young, that is an example of a risk factor. So another example of, so we'll come back to the child development ones. When I was in a really big accident and really demolished my knee and it had to have a couple surgeries, I was told that now, because of that, because of the different things that were done to it, and that I have, so the accident itself, as well as the treatments, as well as the kinds of things that I've had to do to get back to be able to walk, essentially now all of those risk factors pile up and interact, so I am now super likely to get arthritis, specifically in that knee. That's probably where it'll happen first. So another example of interactions. But there are family variables. So death of the family, like of a parent or a sibling, family or parents that you're not securely attached to, abuse in the school, discrimination or bullying. These kinds of things are examples of risk factors. I'm not going to read all of these, but discrimination in a community, homelessness, these are examples of risk factors that if you pile up, add these risk factors on, it puts you at a much harder time in life because they're interacting and making it much more difficult for you to do things like get your basic needs met. So just another practical example, real life example of interactions. So it might not be any one of these leads absolutely all the time to some kind of negative outcome, but the more of these you add up together, they work together in a really negative way. That being said, there are also protective factors. Things that we can do like having secure attachments, having positive relationships, things that we can do in the school or in the community to protect from these risk factors as well, so they can interact in the opposite direction, pushing towards more positive outcomes. So here are some of those protective factors. So secure attachment in childhood, having positive attitudes, experiencing success and achievement and gaining that self-efficacy, having affection and supportive parenting, a positive school climate. And so basically positive school climate is just overall that the people in the school do not allow discrimination, bullying, things like that. They're really positive. They focus on building a community within that school. So in the community itself, having good housing, having high standards of living, these are all protective factors. And in some cases, they're exactly the opposite of the risk factors. In some cases, it's they can kind of work opposed to each other. So you might have one abusive parent and a secure attachment to another parent, for example. Those aren't directly fighting one another, but the protective factors protect against the potential for bad things from the risk factors. So these are examples of actual interactions. So human life, human development, human experience is pretty complicated. So learning about how things interact, how A plus B plus C equals J, is very important. So which of these have the biggest effect, do you think? Which of these interacting together can cause a positive or a negative effect? So that's what interaction is all about, is really measuring and figuring out, well, let's say someone has a socioeconomic disadvantage. What kind of protective factors specifically work the best to overcome that disadvantage? So here's another example. Let's say you have poverty or psychosocial risk factors, central nervous system development and function. All of these are related to your sensory motor, your socio-emotional, and your cognitive and language development. So it's just another example of how these work together. This is a more specific model showing that these are related. This might lead to this, this might lead to this, this might lead to this, that kind of thing. So it's a little different way to look at this model, but hopefully you have a good sense of how important interactions really are in doing the science of psychology. Up to this point, with multiple correlation, we kind of get at this, things being more complicated, there's more variables interacting at any given time. But here, as we're coming to the end of the class and the book, we're really focusing in on there these basics that you've learned in research methods, now we'll take them and really look at interactions and really see how multiple things may cause another thing. And that's how a lot of research is done today. Less of those simple experiments, more of these more complicated things to see exactly how this piece might work into this system for some specific outcome. And again, that goes back to any given study tends to be really pretty focused and testing some specific hypotheses, while the theory might be this entire model, or even more than the entire model. Any given study might be focusing on a couple little specific aspects. All right, so here we see the big theoretical model of child development. So we could pick out these specific relationships from this model, but a study of these specific relationships is a more specific thing than trying to look at this entire model. So hopefully you can see how all of these combined focuses can help in any given study. So how might gender expression affect and interact with socioeconomic status? How does any given culture influence parenting? So these kinds of interactions are all built into this model and this theory, and any given study might be really specific about some exact specific aspects of interactions between specific variables. But for any of these, it's how we get at this complicated assortment of what humans do. So interaction is really similar to a term you might have heard of just in lay conversation. So you might have heard the term intersectionality. This is essentially a lay person way to talk about interactions. So intersectionality is defined as the interconnected, I probably should have made this little image bigger. Hopefully you can read it on your screens. Intersectionality is the interconnected nature of social categorization, such as race, class, and gender, as they apply to any given individual or group. So regarded as creating overlapping and interdependent systems of discrimination or disadvantage. So this is an example of looking at race, class, gender, those three variables, in relation to an outcome of discrimination or disadvantage. So the interaction of these things. So hopefully this kind of gives you an idea of exactly how we might as scientists look at how multiple variables are interacting. So hopefully you're understanding that most things like discrimination and disadvantage are caused not just by one cause, but by multiple causes together, some of those causes adding on to like the terrible things leading to disadvantage, or some things might be protective factors as well. So this is just, intersectionality is maybe a term you've heard of that's really, really similar to what we're talking about in relation to interaction. So just as those demographics of race, class, and gender can lead to those protective factors, demographics of race, class, and gender can lead to protective or risk factors together. So most human behaviors are affected by more than two variables in any given situation. So the social pressures of the group plus your biology. So going back to this model, this is looking at big aspects like the big level interactions. This specific study still looking at quite a few interactions, right? But it is a lot more specific than this one, right? This one's really big and broad. This is the whole theory, versus intersectionality is specifically focusing on these couple variables relating to these specific kind of outcomes. So it's still interaction. All these are really great examples of interactions. So with this, some interactions require more than two variables to make an effect. So you might need variable B and D for E to then change. So and if either B or D is not there, E might not change. The effect of each of these variables is measured as effect size. And we've talked about effect size a couple times briefly in the class. We'll dive into it in a lot more depth right now. So we can measure the effect size through things like multiple correlation. We can also look at it in causal variables through experiments like how much did one group improve or how different was one group than another group. So multiple correlation, multiple regression can also give us effect size. So as a reminder, multiple regression looks at correlation relationships. So again, this is not causal for multiple regression. You look at the relationship between some outcome variable and the multiple independent variables. This was one that we used in class earlier. So this was like your oxygen intake, and you could predict that based on your gender, your heart rate, your weight, your age. So you're not causing a change in someone's age. I don't think you've got a time machine to cause that change, but we can look at the relationship between age and how much oxygen your lungs can actually process. So, do they all have the same relationship together or apart with oxygen? Are some of those more important? Like, is your weight more important to how much oxygen you're processing? Just as a question that you might ask. I don't actually know which of these variables is the strongest impact. So I guess I could look at the effect size right here and decide. But this is just from one study. This isn't overall. So with this, mediation helps explain how two variables are related. So mediation is like this here. So x can lead to y, but x can also lead to this one, which can also help lead to y. So sleep quality and its effect on academic achievement can be mediated by alertness. So let's say you have really good sleep, you'll probably do really well on a test. If you have really good sleep and you're feeling very alert, you'll do even better on the test, right? So there can be full and partial mediators. So the full mediator completely explains the relationship. Let's say you slept really well, but you feel absolutely not alert at all. Maybe you'll still do really poorly on the test because now it's back down to kind of all taken on by that alertness. But partial relationships still can exist without that mediator, so that sleep may still affect no matter what your alertness level is. So moderation affects the strength or direction of a relationship. So it's like this over here. So x leads to y, and then the moderator can completely cancel out or reverse that relationship. So sleep quality and academic achievement can be moderated by mental health. So let's say you've got really poor mental health. You're super anxious, for example. You get really good sleep the night before a test, but because of your anxiety, even though you got good sleep, you do really poorly on the test. So even though there generally is a relationship between sleep quality and academic achievement, this moderator variable, your anxiety here, completely destroyed that relationship that usually exists. It moderated it. So a certain mental health condition could make the relationship stronger as well. So maybe you have very healthy mental health. So even though you didn't get good sleep, your mental health is really good and you end up doing well on the test anyway. As some little examples. So mediation explains how the two variables are related. Moderation affects the strength of the relationship between those two variables. So this is a little model of an independent variable and the outcome variable. There could be a mediator. There could also be a moderator. So moderator could move to over here or even over here. So you can see from this, hopefully, that basically any kind of relationship we could test to see, is this moderating? Is this mediating between A and F? So this is the theory of planned behavior. I don't think we've shown this in this class. I generally show it in the social psych chapters of general psychology. But we have an intention to behave. But we also have behavior. Right? So let's say you really intend to vote. So you intend to vote in the election, but it can be moderated by your actual behavioral control. So let's say you really want to vote, you plan on voting, you think voting's good. So you're intending to vote, but your ballot never actually comes in the mail. And you're working the day of the election, you just cannot get to the voting booth. Then your actual behavioral control completely took control of this relationship. While usually intending to vote, you'll probably go and vote. Your behavioral control moderated that. What goes into that intention, though, are some mediators, right? Your attitude towards the behavior. Your perceived behavioral control. So do you think that you can go vote, or did you realize, oh no, it didn't, my ballot didn't come, or something like that? So this is a model that is used in social psychology to predict behaviors. It's really relevant for lots of different kinds of behaviors: pro-social behaviors, voting behaviors, volunteering behaviors. Lots of things you can look at using this model and try to pinpoint, well, for any given behavior, what has the strongest effect, what has the strongest effect size. So let's say we wanted the behavior to be something like help seeking when you are suffering from depression. So that would be a really good behavior to do, to seek out help, to call to get therapy, reach out to a friend even. Things like that are a behavior we would want to encourage. So what's the most important pieces here? Is the attitude the thing we should focus on? Is that the biggest effect that maybe if we did an intervention we should work on that? Should we work on the subjective norm? Or should we look at your perceived behavioral control? So a lot of research shows that what we should do is usually people have a pretty positive attitude even when they're suffering from depression towards seeking help. They even know that people around them might have the norm to seek for help, but they don't feel like they can do it. It's a symptom of depression that they just don't have the perceived behavioral control to go and actually seek out help. So that might be the one to intervene on because it seems to be having a really big impact. So that's what you can do for all kinds of behaviors, is use these kind of models, use mediation, moderation, use the interaction and measure it to try and figure out how to do things and how to make results. So we've got some funny examples using donuts to see how donuts and an experiment with donuts might change people's ability to do things. All right, so these are kind of silly examples, but hopefully they're understandable. We're looking at two independent variables. So this is an experiment. Independent variables are the ones you manipulate. So in this one, we're manipulating donuts, and you can't actually manipulate age, but let's just pretend we can manipulate age. So this is the term for this is actually different. It's not independent variable. It would be a blocked variable, if I'm not mistaken, or maybe that word's just on my mind. But anyway, for our purposes, we're pretending that we can manipulate age, that we can make people different ages. So these are our independent variables: donuts, age, and our DV, our dependent variable, dependent word, it was gone, is productivity. So kind of silly examples, but hopefully they get the idea across of two independent variables working together. So we have 8-year-olds versus 38-year-olds. So with this, we've got the ability to age this kid up to now 38. So we have 8-year-olds and 38-year-olds. We have two conditions: one where we give people donuts, one where we do not give them donuts. So we give some 8-year-olds donuts, we give some 8-year-olds no donuts, we give some 38-year-olds donuts, we give some 38-year-olds no donuts. So this is 4 groups. So it's a more complicated experiment than our simple rooms of loud noises and no loud noises with a DV of test score. You could do this kind of model by, say, maybe this is loud noise, no loud noise, this is 1 hour of tutoring, this is 2 hours of tutoring. It's the same kind of thing. So this is one way to see how variables interact with one another. All right, so a main effect is the effect of one independent variable. An interaction is when you're looking for what is happening between the independent variables. And so this isn't available with simple experimental designs. You can't see the interaction. If you're using simple experiments, it has to be with at least 2 independent variables. You can use more than 2 independent variables. You can use multiple levels of some of those variables, and we'll do that. So is there a difference? Is there a difference here between donuts and no donuts? Then yes, that's kind of like a simple experiment, right? You're just comparing here donuts versus no donuts, and you don't care about the age. You get the mean here, you get the mean here, and you average those together for this. Get the mean here and the mean here, you average it together for this. In our example, the effect of having donuts versus no donuts on productivity. And so for productivity, let's make it pretty silly. Let's say how many Lego creations you can build in 15 minutes. And that's your measure of productivity. 1, you get a score of 1. You build 10, you get a score of 10. So that's our measure of productivity. Is that a great measure of productivity? I mean, if you're measuring 8-year-olds, probably, right? So here, we can also look at the main effect of age. So ignoring the donuts, so some of these people had donuts, some of these people did not have donuts. We take the 8-year-olds mean here, the 8-year-olds mean here, we average it together. and we see, hey, is this different than this average? That would give us the main effect. That would tell us if that would tell us if age is having an effect. So again, we can go back. We can look just at the effect of donuts, the main effect of donuts. We can look at just the main effect of age. Is there a difference? Yes, that means there's a main effect. Interactions, look at how those variables interact, how age and donuts interact. So we can't see that with simple experiments, and with this we really have to graph our data. So for the y-axis, which is this one, I always have to remind myself, we put the means for the dependent variables. So x-axis is variable 1, and the lines are variable 2. Especially if it's nominal, use this as the lines. So for our example, the age is a good example of a nominal variable, or a categorical variable for age. So we'll use that for lines. And then you check, is there a difference in the slope of the line? Are they parallel? Are they crossing? Are they coming to a point? Are they parallel or not? If there's a difference in slope, it says there's an interaction. So let's get some data here. The 8-year-olds, they ate donuts. And the 8-year-olds who ate donuts only made 2 Lego creations in the 15 minutes. The 8-year-olds who had no donuts made 5 Lego creations in the time. Versus the 38-year-olds who ate donuts, they made 8 Lego creations in the 15 minutes. The 38-year-olds who had no donuts made 5 Lego creations in that time. So kind of a silly example, right? But let's graph this out. Let's graph this out with lines. So that's what this looks like. We have the dependent variable here of Lego creations. We have the 8-year-olds over here, the 38-year-olds over here. So again, the 8-year-olds who had donuts made 2. You can see that is at 2. The 38-year-olds who had donuts, they made 8. So that is 8. And both of the groups who had no donuts, made 5. So this is no donuts, this is donuts. Hopefully this graph is pretty understandable. And we can see here that these lines are not parallel. There is an interaction. There is some kind of interaction of having both these variables at the same time. So we would say this in a really specific scientific way to just basically spell out in words what is happening in our graph. Since I have 2 screens, maybe I should try to put the graph on this side and the words on this side. That's not a bad idea. I'm going to try to do that really quick. Alright, so I actually recorded all this again, but when I made that switch, I accidentally pushed mute and forgot to unpush mute. So this will be my second time through this. But here is the graph again. So this is the interaction graph, and essentially we're spelling this out. So the main effect of age was qualified by an interaction of donuts and age. So now we start describing the interaction. For those who did not eat donuts, there was no difference between 8 and 38-year-olds. That's what we see right here, right? There's no difference at this point. But for those who did eat donuts, 38-year-olds were more productive than 8-year-olds. So 38-year-olds did the absolute best. So that's one way to describe this interaction. It's a really specific way to really spell out what you see in this graph in words. That helps a reader really identify what you are talking about, which one was best, which one was worse, because you might not have this graph actually in your paper. So here's another way to say that. The main effect of age was qualified by an interaction of donuts and age. All right, and here we start it. So for the 38-year-olds, eating donuts increased productivity. And we see that right here, right? It increased. From the baseline of no donuts, it increased productivity. Whereas for 8-year-olds, eating donuts decreased productivity. And we see that, right? This is a causal experiment. We've had a group that was 38 and had no donuts. We had a group that was 38 and had donuts. We had 8-year-olds who had no donuts, 8-year-olds who had donuts. So we did a true experiment here. So this is causal data. So we have a causal, we have increases and decreases that we have measured with our causal data. All right, now if we want to add more levels, we can just do that. We can add more levels to the variables. So if we wanted 0 donuts, 1 donut, 2 donuts, if we wanted 3 ages, we can do that. We just have to specify those things in our really spelled out way. So it's the same process, just a couple more steps. Let's use this example again. here we have the data. We have 10-year-olds with no donuts, 10-year-olds with 1 donut, and 10-year-olds with 2 donuts. We have 25-year-olds now with 5 donuts, we have 25-year-olds with no donuts, 25-year-olds with 1 donut, and 25-year-olds with 2 donuts. So each of these boxes represents a different group of people. So this group right here were 40-year-olds who ate 1 donut. This group was 40-year-olds who ate 2 donuts. So from this, you might already be able to pinpoint, well, who did the best? Who was the most productive? Well, it was the 40-year-olds who had 2 donuts. Who was the very least productive? The 10-year-olds who had 2 donuts. So that might be an interaction, right? We might have an interaction here, but first we've got to make sure what are the main effects. So again, we get let's check donuts first. So what's the main effect? Do donuts have an impact no matter what your age is? So we are parceling out the data about age. We are only concerned with donuts right now. So for people who had no donuts, they made on average 5 Lego creations. For people who had 1 donut, they made on average, again, 5 Lego creations. For people who had 2 donuts, they made on average 5 Lego creations. So there is no main effect of donuts. If we were doing a simple experiment and that's all we were testing is donuts, we would see, nope, donuts didn't have any change. It didn't matter if you ate no or 2 donuts. But that would be a real loss, right? Because it looks like something's happening here. Now let's look and see if there's a main effect of age. So for this one, we look at the ages. So for the 10-year-olds, what's their average? 3. 3-year-old or 10-year-olds made an average of 3 Lego creations. 25-year-olds made an average of 5 Lego creations. 40-year-olds made an average of 7. So 40-year-olds were the most productive over 25-year-olds over 10-year-olds. So there is a main effect of age. Now remember, we've got to graph them to see if there's an interaction. So I'm going to move this data over to this side. So here's our data, and here's our first graph here. So I'm covering up that 9. But here we have all these points, right? So for no donuts, all the faces should be on 5. They are. When people eat 1 donut, the 10-year-olds should have 3. The 25-year-olds should have 5, and the 40-year-olds should have 7. And that's what we see right here. And then for 2 donuts, we've got 1, 5, and 9, 1, 5, and 9. So here we've got our graph. Are these lines parallel? Well, obviously not. There is an interaction, right? Now you might ask, well, what if we did the different thing? What if we put the faces on the bottom rather than the donuts on that bottom axis? So the x-axis. Would we still find an interaction? Yes, absolutely. It will look different, but we will find an interaction. So this is that graph. So this is the same data that we were looking at before. So for 25-year-olds with 1 donut, here's 25-year-olds, here's 1 donut. You can see they had 5. So this is a line for 1 donut, this is a line for 2 donuts, and this is a line for 0 donuts. So are these lines parallel? No. So there is an interaction. So it looks a little different because we moved the variables, right? These variables are down here on the x-axis versus here they were as part of the line. But we still see an interaction. So let's go back to here, and I will go to this. So when we're looking at this, is there a main effect of age? So if there was a main effect of age, we already saw that the 40-year-olds were the most productive, 25-year-olds were also pretty productive, and they were all more productive than the 10-year-olds. There was no main effect of donuts. No matter if you have no donuts, 1 donut, or 2 donuts, taking out the data about age, you have no main effect. It doesn't matter if you have 1, 2, or no donuts. The main effect of donuts doesn't exist. It has to be included. It has to interact with age. So there was an interaction between age and donuts. For 10-year-olds, the more donuts they ate, the less productive they were. For 25-year-olds, donuts didn't affect productivity. They stayed making 5 Lego creations in that time. And for 40-year-olds, the more donuts they ate, the more productive they were. So I do wonder if we kept giving these 40-year-olds, or if we gave them 3 donuts, would they be even more productive, or would there be a point where it kind of plateaued out and maybe they get sick for too much sugar and start producing less? And those are the things you want to test as you're really looking at actual human behavior. Are how are these things interacting? How does one variable affect another? How do they work together to come to this? Because if we just did the experiments with donuts, we would see no effect. But when we look at donuts and age, we can see that, yeah, the 40-year-olds, they should get some donuts. The 10-year-olds, like, one, don't do child labor. But if we wanted to make the 10-year-olds make more Legos, we shouldn't be giving them donuts. We should give them 0 donuts. So this can be used, you can take this kind of example to something more real life, like medicines. There's a bunch of different painkillers that work better when they interact with caffeine. So, for example, they've tested it with, say, a specific dose of caffeine pill plus the medicine, and people show more pain relieved. So, really good example of interaction there. Interaction of the risk factors, protective factors. You can do these kinds of causal studies for some of them, for some of those risk factors. That's going to be really difficult to do in an ethical way. But you can get good data to say how things are all interacting. Otherwise, we might not know that 40-year-olds, we should be giving them donuts to make more Lego creations. All right, so now let's move over to talking about effect sizes. We'll talk about them in a lot more detail than we have before. Basically, it's a measure we use to determine which variables have a strong or weak effect on variables. And so when we're talking about correlations, it's the strength of the association between the variables. When we're talking about causal data, it's the strength of the intervention, it's the bigness of the difference, that kind of thing. So in an experiment, the effect size is the size of the treatment effect. How much advantage did you get from the treatment? How many points did you score better from having 2 hours of tutoring? How much pain was relieved from the medicine? That's the effect size of the treatment effect. In a non-experiment, like a correlational study, the strength of the relationship between the variables. And that might sound similar. A correlation is an example of a non-experimental effect size. How strong is that relationship between those variables? So, experiment is the magnitude of the effect of the independent variable on the dependent variable. So some things that we look at for effect size, the mean difference is a measure of effect size. So you scored, let's say your group on average in the quiet room scored a 80 on the test. In the loud room, you scored a 70 on the test on average. So the mean difference is 10 points. So that's not a standardized measure. You can't compare it to another group or another class that did that same study. This is why we use something called Cohen's d, and it is a standardized measure. Basically, you take the raw scores divided by the standard deviation. The actual calculation of it is not that complicated, but that's not the point of this discussion. The point is the Cohen's d you can compare across studies. Meta-analysis will look at that d and they will compare them to see what is the actual true effect of this medicine, of this treatment, of this thing. So you can compare that standardized Cohen's d statistic across separate studies. So if I do a study of purpose in life here today, and someone else does it 4 years from now, they can compare their result to my effect size. Because those samples that got that mean difference, they're going to be different, right? So it might give you some idea, but it's not as useful as the effect size that's standardized. So Cohen's d is what you want to use to compare multiple studies. For a non-experiment, the examples that we have are correlation, so the R. And then for multiple correlation, we have the R squared, the percent of the variance explained. So you've already heard about R. You know that for a correlation, it goes from -1 to +1. Any other effect size, like Cohen's d, goes from 0 to +1. And the closer it is to 1.00, the stronger that effect. So this is going to explain some of the calculations of effect size in an experiment. I think I needed to be a little more clear about my note here. I think I'm watching up to 1:45 in class so that we can get a better sense. Again, you don't need to know how to calculate these things, but this will help you wrap your head around the effect size, I hope.
In this tutorial, I'm going to discuss Cohen d, or effect size. I'm going to tell you some introductory information about it, as well as how to interpret the results. And finally, I'll use some real numbers to calculate a D, or Cohen D, or effect size. So let's imagine we have a control group. Put that in green, and we also have mean right there. An experimental group, and I'll put that in blue. The Cohen D measures the distance.
So before they continue, you can imagine the control group is our group in the quiet room taking the test, and the experimental group is the group that was in the loud room. Maybe since we see the experimental group scored higher here, maybe it's a room playing classical music. Maybe the quiet room will not do as well as if you have soft classical music playing. So that's our experimental group here.
That the means of the two groups have shifted, and it's measured in standard deviations. How many standard deviations has it shifted? And it can shift this way, negative, and it can also shift positive, of course. It's frequently labeled Cohen D like this. And all you need is the mean for both groups and the standard deviations. The calculation is relatively simple to do. Let me put this back to the control group and also the experimental group here. D is equal to the mean of the experimental group minus mean of the control group divided by the standard deviation. And we always take the absolute value of this top term, so it's always a positive number. And in this case, we're making the assumption that the standard deviations between the two groups are equal. It is considered a really small effect when...
Alright, so that is the calculation. Hopefully that helps make it a little bit more clear. Again, it's a pretty simple calculation. You don't have to do the calculation, but hopefully you have a better understanding. So this is our group that was in a quiet room. This is our group that is in a room with soft classical music, and they score some... Sorry, I just threw my microphone across the room. They score some points above the control group, so we want to see, well, what is the Cohen's D effect size here? So we compare the mean difference to the standard deviation, so now we have a standardized difference score for this test. So if someone else wants to test this in their school, they could get a standardized score, and we can then compare those standardized scores. Maybe our D is 0.85. It doesn't look like it is. It's not that big of a difference. But let's say it is. Then we can compare it to theirs. Theirs was 0.75, and then maybe another school does it 0.3. And then we can compare those, put them together in a meta-analysis to see what is the actual effect across all schools of doing classical music versus no music. So that is what Cohen's D is. It's a measure of effect size in experiments, and it's really, really useful to see the strength of things. So let's use another example. We have this chart from that, or that image from that video. Let's say we are doing a smoking program. We want people to stop smoking. The control group has a mean, the smoking program, their mean is 0.5. The control group has a mean of 12. The actual calculations, the effect size, actually I can't remember offhand. I think I might have just made up these numbers rather than actually calculated them. But let's say this is the effect size of 0.9, just to give you a sense. Let's say your mean difference is 9 versus 12, so a littler difference. You had some effect, but not as big of an impact. Your smoking program worked to decrease smoking, but not as much as this smoking program. So maybe this effect size is 0.48. Then maybe your effect size is basically non-existent. Your change might be a result of chance. Your effect size would be very low. Remember, we're trying to get to 1.00 is a perfect strongest effect. So this is a very big effect. This is still a pretty large effect in social sciences, and this is essentially a non-existent effect. A very weak effect. So these are not actually numbers of how these would be calculated, because obviously I don't have the standard deviations here. This is just a visual example to show you this program is obviously working better than this program, and the Cohen's d reflects that in a standardized way, so you can compare your program 1 and program 2 to someone else's program 1 and 2's effect sizes. All right, so which program worked best? In social sciences, usually we call something that's 0.60 plus a large effect, something that's about 0.40 a medium effect, and something smaller than 0.3 a small effect, or even down to like 0.1 as non-existent effect. So the types of study that you do and how many variables you're using affects what you will expect. So if you are looking at the effect of 10 variables together, having an effect size of like 0.3 with all those 10 variables might be really important, might not be important, right? So just because it's a large effect or a small effect, that small effect, for example, the effect size of when you get older and you might have heart problems taking a baby aspirin every day, the effect size is very small, but it actually translates to many years of life lived longer on average. So a small effect can be important. A large effect might not be important, but it does show that one variable is having a big effect, or the interaction together might be having a big effect. So for non-experiments, the correlation of R of 50, you basically square that. You can look that you're explaining about 25% of the variance on 1 dV with your IV with your predictor variable. So it's great to use effect size in correlational studies. You can see how much effect one variable is having in another when we look at a model of correlational studies, like multiple variables and those maps of circles and arrows all around. We'd use effect size to see, well, it looks like this one, this one, this one are all related to each other in this way. This one's more related to these other ones. That could be important. So again, in a non-experiment, this wouldn't be causal data. So regression equations do this. So what is the best predictor of you doing well in graduate school, or what's the best predictor of you doing well in graduate school? Is it your GPA? Is it your reference letters? Is it your extracurricular activities? Is it your seeking out internships? Like, programs have regression equations to predict how well you'll do your first year. Which of those is the biggest effect? I don't actually know. So, but you can use a regression equation to figure it out. So a good example of this is, let's look at child attachment is related to your adult attachment. It's often moderated by parenting style. So let's say this effect size between child attachment and adult attachment is 0.90. That means your R squared is 81%. So you can mostly predict your adult attachment from child attachment. Let's change these arrows. So the arrows are all getting different shapes. Here it's more mediated. So now the direct effect of child attachment and adult attachment is smaller. The R is 0.48. It means your R squared is 0.23. So it seems to be less of an impact of just child attachment. Parenting style in this example has more of an impact. An impact might be the wrong word. Has more of a relationship than it did here. So you can see the arrows getting smaller and bigger across these two examples. Now let's look at this example. Here, the relationship between child attachment and adult attachment is pretty much entirely mediated by parenting style. In this case, this relationship can better be explained by the relationship between child attachment, parenting style, and parenting style to adult attachment. So with regression equations, you can see, what is it? Is it this? Is it this? Is it this? And depending on what you find, might tell you what to focus your energy on, what to focus your next studies on, those kinds of things. All right, so the take-home points of this is, very rarely is there one single causative agent that predicts behavior. Human experience is pretty complex. There's lots of things that go into it. So in other sciences, there's lots of variables that go into a star and planets being formed, for example. All those variables can be looked at in these kinds of ways with effect sizes and correlations, or experimentally in interactions. So maybe not the planet example. So the effect one variable has on any others might depend on the other variables. So your happiness and purpose in life might impact your career seeking behavior. And it has to be both of those are working and depending on one another for the eventual outcome. So it's almost always some combination of behaviors, or sorry, some combination of variables that influence behavior. It's not just one or two, it might be three or four. So to do these more complex analysis, we need to look at regressions, we need to look at interactions. So regressions are for correlational data, where you're looking at relationships. Interactions is for causal data, where you're looking at what things cause another thing. So once multiple causes of a problem are found, then you can figure out solutions. Do you aim at just one piece of the problem? Is that the most important part of the problem? Is that where you should focus your attention? Or do you do an intervention that hits at multiple parts of the problem? Or do you work with a team and other people around in the community and do multiple kinds of interventions at the same time? So policies. Do you do one sweeping policy that affects absolutely everything? Or do you do multiple smaller policies to change little bits of certain things? So that is hopefully a lot of information that with some, even though some silly donut examples and things like that, hopefully it helped you understand how interaction works in human subjects research. Hopefully it helps you understand how regressions work in psychology research as well, and see how it can be really important and really useful. So we just saw a little bit of the math, and that was actually really simple math too. More of the complicated math is basically done by computers, so don't be scared of it. Understanding the concepts is the biggest thing. If you understand the concepts, you'll be able to do the kinds of statistical analyses. But the big thing, the big takeaway is that behaviors are caused by multiple things. These are the kinds of tools and techniques that we've got to use to figure out how things are affecting other things. All right, have a good day.